Hello everyone, my name is Roland Martinez,
And my name is Alec Tolentino.
and today we are going to show you our video presentation for the final documentation of Activity 5 in ECE 122, L Section E02, or the Digital Communications Laboratory. And the Activity 5 is entitled Amplitude Shift Keying, and our instructor is Engineer Marian M. Sihel. So first is the theories and concepts regarding the ASK or amplitude shift keying. First, we need to define the modulation or the process of changing the characteristics of the wave to be transmitted by superimposing the message signal on the high frequency signal. In this process, the modulating signal is enveloped by the carrier signal. So we already tackled the different types of modulation. For analog, we have the amplitude modulation, frequency modulation, and phase modulation, where for the AM or the amplitude modulation, the amplitude is enveloped by the carrier wave. And for the frequency is varied using the carrier wave, and for the phase modulation is the non-direct or FM, or the phase is varied by the carrier wave. So what is ASK or amplitude shift keying? So this is a type of the or the counterpart of the amplitude modulation, but in digital modulation, wherein the ASK refers to a type of amplitude modulation that assigns bit values to discrete amplitude levels. The carrier signal is then modulated among the members of a set of discrete values to transmit information. And amplitude shift keying in the context of digital communications is a modulation process which imparts to sinusoid two or more discrete amplitude levels, or also called as on-off keying or OOK. These are related to the number of levels adapted by the digital message. For a binary message sequence, there are two levels, one of which is typically 0. Thus, the modulated waveform consists of bursts of a sinusoid. And in the next figure, we will see that the binary SK signal for lower is 0, that together with the binary sequence which is initiated in upper as 1, and neither signal has been band limited. So this is a figure of the block diagram for the ASK generation or the modulator, where the input signal is sinusoidal carrier with a unipolar binary sequence message that is going to the mixer, and the output is ASK or the output band limited ASK. So next is the figure where the ASK can be varied by a time period, where you can see that the amplitudes here on the left or the duty cycle on the left side is smaller than the duty cycle on the right side, where the sinusoid is much longer, and the pulse wave or square wave on the right side is longer compared to the left side, where the amplitude is 1 while the minimum is 0. So this is where ASK is band limited using a low pass filter or a band pass filter. So the pulse width or the pulse signal is fed into a low pass filter and on a mixer together with a sinusoidal generator. The output will be fed also into the band pass filter, and the resulting output signal is amplitude shift keying with band limiting. So as you can see here on the figure, that the message is on the lower side or or the lower side wherein the pulse is in wherein the message is in pulse form. Then the output signal is in the form of the sinusoidal wave with different envelope duration, where the sinusoidal wave has different length, and the band limited message is on the middle, where you can see there are some sinusoidal or charging of the signal, and the amplitude is varied. So you can see here the block diagram, or the simplest block diagram of the ASK, where the input signal is a pulse, where 1 and 0 in form of 1 and 0 or the digital signal. Then the output signal in ASK form is in sinusoidal form, where there are durations that the amplitude is positive or on, and there is a duration that the signal is off or no sinusoidal wave at all. Then, as you can see, the input binary is in 1 and 0s. Then this is the ASK modulated output wave on the lower part. So in this activity, we are asked to design a block diagram for the ASK or the ASK modulator using the MATLAB Simulink. And as you can see in the slide or in the figure, that the input signals are sine wave and a pulse generator, and they are fed into a product block, and each output signals are monitored using scopes. So for scope 1 and scope 2 for the product. So in part 2, we are asked to use the MATLAB editor using the line of codes that are given in the manual, and or the function file that is already uploaded or given to us, so that we can generate the plots using the program or the MATLAB editor. And on the output, we must show the figures such as the carrier signal, pulse signal, and the ASK signal. So in part 3, the program used in part 2 is also used in part 3, where we added the additional line of codes for the plotting of the frequency domain of the carrier signals, pulse signal, and the ASK signal. So before we are going to show the results for the Simulink and the MATLAB editor results, we are going to show you our time-lapse video for the demonstration of the simulation of block diagrams and the live editor code used in this activity.
Hi everyone, my name is Roland Martinez, and this is a video demonstration of the Activity 5 in ECE 122, Section E02, which is the amplitude shift keying using the MATLAB Simulink. So in this video demonstration, I will create a block diagram for the amplitude shift keying and simulate its result. So let's get started. to run the simulation, we need to click the Control T or Run button. So checking the simulation result using the scopes. For sine wave 1, we need to use the scope 1 or scope. And for scope 2, scope 1, so we can differentiate the outputs for the different scopes. For scope for the sine wave is a sinusoidal wave. Zoom in so that we can observe. So we can observe that the output for the scope or the sine wave 1 is a sinusoidal wave with a attenuation in its wave. And for scope 2 or scope 1, the output is a pulse wave in square wave. For the scope 2 is the ASK output or the amplitude shift keying, where we can observe that this side is the sinusoidal wave and with a 0 amplitude on the middle of each two sides of sinusoidal wave. So for the part 2 of this experiment, I need to copy the original function file or function code from the laboratory manual to the function file as mapua.m, which is already pasted on the file, and this will plot first the carrier signal. So to run this, clicking the run button, it will show the figure 1, which is the carrier signal, and we can add the pulse signal by changing the or adding additional plotting commands or code in the original function file. So copying this so that we can add figure 2 as the pulse signal, and by changing the title and the plot parameter for T and M and pulse signal for the title. So we can run again the code so that we can see the output file, which is the figure 2. Figure 2 shows the square wave signal or the pulse signal with an amplitude of 1 for 1 second. Next is to add additional plotting code for the or function for the ASK signal using the same function or line of codes by changing the parameters. For figure 3, we need to change the parameter for the plot, and that is ASK. And lastly, the title of the plot or the figure. So clicking the run again to show the output signal. So you can see here the output signal or the amplitude shift keying signal with a sinusoidal wave, and at 0.2 the amplitude is at 0 and returns back to 1 at 0.4 until 0.6 and goes back to 0 and repeats the process. So this is the ASK signal, the pulse signal, and the carrier signal. So to continue with part 3 of this laboratory experiment, using the original function askMapua.m file, we need to add the additional line of codes for the part 3. So we can plot the carrier signal, pulse signal, and the ASK signal in its frequency spectrum. So again, clicking the run button to show the figures 4, 5, and 6 for the carrier signal, you can observe that the amplitude of the maximum amplitude of the carrier signal is at 0.5 in its frequency spectrum, while the pulse signal, the amplitude is at 0.6, or the maximum amplitude is at 0.6 for its frequency spectrum. And lastly, the ASK, or the amplitude shift keying signal, the maximum amplitude is 0.3 for its frequency spectrum. So that's the result for the part 3 of this laboratory experiment.
Hello, my name is Alec Tolentino, and I will be demonstrating activity 5, which is amplitude shift keying or ASK. So the objectives of this activity is to be able to create a block diagram that can generate ASK signal on MATLAB Simulink, to be able to modify the parameters of each block of the ASK generator, and to be able to show the plots of the outputs for each block of the ASK generator. So modulation is the process of varying one or more of the properties, which can be the amplitude, frequency, or phase angle of a sinusoidal carrier signal. When the modulating signal is a digital signal, the process is called digital modulation. Amplitude shift keying or ASK is one of the digital modulation techniques wherein the amplitude of the carrier is varied. The amplitudes represents either a 1 or a 0. Amplitude shift keying is the digital counterpart of amplitude modulation or AM. So the procedure is, the step 1 is to create a new Simulink model of an ASK modulator shown below. So now I will be creating the Simulink model for the ASK modulator. So these are the outputs for the Simulink diagram for the scope labeled which is sine wave, then for scope 2 which is the pulse generator, and for the last output is for the product labeled scope 2. So that is all for my demonstration for the building of the Simulink model for activity 5. Thank you.
So for the datasheet activity results for the part 1, the Simulink result is that we are given a block diagram which is a sine wave input and a pulse generator input blocks, and their signals are fed into a product block, and the outputs are monitored in scope 1, scope 2, and scope. And you can see for the scope 1, for the sine wave generator signal, we can see a sinusoidal waveform as the output signal for the sine wave generator. Next is the pulse signal that the pulse generator is produced, and we can see a pulse signal or square wave signal in the plot. And lastly is the ASK signal or the amplitude shifting signal, that is the product of the sinusoidal wave generator and the pulse generator. You can see the amplitudes that there are durations that the amplitude is on or at 1 or -1, and at 0.2 seconds the amplitude is at 0, and it is repeating on this block diagram output. So here we can compare the results using a scope 3. We can fed all the output signal from sine wave 1 pulse generator, and of course the product or the ASK signal of the two input signals. So in the top plot is the sinusoidal wave or the modulating signal, then the ASK signal in the middle, and the pulse generated signal on the lowest part or the last part of this figure.
So proceeding to part 2 of the activity, which is plotting the ASK signals in the time domain, and instead of using the block diagram and the scopes, codes were used instead for this part of the activity. So for the first part of the code, it was all about declaring variables and their values through equations such as the number of samples, time, carrier signal, modulating signal, and ASK signal. This was then followed by codes that plots the carrier signal, modulating signal, and ASK signal by using the declared variables. So for the first part, the modulating signal graph, carrier signal graph, which it shows a smooth sine wave signal with a constant peak-to-peak voltage of 2 volts and a constant frequency of 15 Hz. Such results can be attributed to the setting of the generator, in which the amplitude is set to 1 and the angular frequency 2 pi f, where f is for the frequency, which is set to 2 pi multiplied by 15, which is why the frequency of the carrier signal is 15 Hz. Next is the carrier signal graph, which shows a square wave that has an amplitude of 1, in which it can be seen that the duration of every highs and lows of the signal are equal. This is because the pulse width of the generator was set to 50% of the period. Therefore, the duration of the highs will only be for half of the period. Then the other half would be a low output. It can be seen also that the signal is from 0 to 1 and vice versa only, which implies that the signal generated is a unipolar signal. Next is for the output ASK signal, which shows two alternating outputs, wherein first it shows a constant amplitude and a constant frequency sine wave signal, and the other one is just a flat zero output. This is because since the modulating signal is at high output first, which is 1 volt, then multiplying this to the carrier signal would just copy the instantaneous value of the sine wave carrier signal, which is why for the part wherein there's an output, the signal is just identical to the carrier signal. Then on the other hand, since the low output of the carrier signal is 0, multiplying this to the sine wave carrier signal will also produce 0, regardless of what instantaneous value of the carrier signal is. So after plotting these graphs, it is observed that the signals are the same with the signals from the part 1, wherein the scopes were used compared to the codes were used in part 2. Moving on to part 3, which is plotting the ASK signals in the frequency domain. Again, in this part, we did not use the block diagram, but we used the pre-made codes given in the manual, which again use the declared variables in the first part of the code in part 2. Entering the code, 3 figures were displayed showing the carrier signal, modulating signal, and the ASK signal in the frequency domain. So from the results, it can be seen that the carrier signal has a high amplitude output at 15 Hz, while the amplitude at other frequencies are almost 0. This is expected since the carrier signal was set to operate at 15 Hz based on parts 1 and part 2. Next is for the modulating signal. The highest amplitude is in the 0 Hz frequency, and since it is a square wave, the frequency components can be seen at every 2.5 Hz, since it is the operating frequency set in the generator. Then lastly, the ASK signal frequency response. In the figure, it shows that the highest amplitude is at 15 Hz, which means that after the mixing of the carrier and modulating signal, the operating frequency became 15 Hz, while at other frequencies, the circuit is still operating, but it does not have a high output as implied by the sidebands, which has significantly lower amplitude than the 15 Hz output. Then it can also be seen that the amplitude is 0.3. This is because by going back to the highest amplitude of the carrier and modulating signal, the values are 0.5 and 0.6 due to the multiplication of signals, which is the product is an amplitude of 0.3. So in conclusion, amplitude shift keying is simply the mixing of a digital modulating signal and an analog carrier signal through multiplication. Even if the block diagram created in this activity seems simple, since it only used a sine wave generator, pulse generator, product block, and 3 scopes, the actual circuit could be really complex since MATLAB can only made it easy by providing blocks. But in reality, generating and mixing the signals would require a design of combinations of different electronic components such as resistors, op-amps, capacitors, and etc. Then using a unipolar digital modulating signal would result to an ASK signal wherein the output would be 0 every time the digital modulating signal is at its low state output. Then an analog signal operating in a constant frequency would result to a frequency response wherein a high amplitude output would be on the operating frequency, while the other side bands will have almost zero amplitude since the signal is just set to operate at a certain frequency. Then a square signal operating at a certain frequency would result to a frequency response wherein even if there is many sidebands, the only significant sidebands would only be found at certain points of the frequency spectrum based on the operating frequency set. And that concludes our presentation for this activity. Thank you.